10 IPs poisoned our autocomplete cache with offensive suggestions in 1 hour. The system stored any query appearing more than 100 times in the last hour without checking its content. Attackers exploited this by flooding offensive queries, and soon every user saw inappropriate suggestions. Here's exactly why. But first, let's understand how autocomplete works. Welcome to TheCodeForge. Before we dig into that production issue, let's design a search autocomplete. A search autocomplete system predicts completions as users type, serving top K suggestions within 50 ms. The core data structure is a trie for prefix lookups, often combined with prefix hashing for memory and speed trade-offs. Ranking blends global popularity, personal history, and recency. A trie node stores children, a flag for end-of-word, frequency, and a priority queue for top K suggestions. This allows O-K prefix lookup and fast retrieval of top completions. Here's the Java implementation of a trie node. It uses a hash map for children, a boolean for end-of-word, an integer frequency, and a priority queue for top K completions. In production, you'd maintain a bounded top K heap per node. Two dominant approaches, the classic trie and prefix hashing. A trie offers deterministic lookups, but memory can balloon. Prefix hashing uses a hash map keyed by prefix strings, simpler and more cache-friendly, but loses prefix sharing benefits. Real systems often hybridize. Here's a simple prefix hash store using a concurrent hash map. The key is the first 3 characters of the prefix. Note that updates must be atomic. Use replace with CAS to avoid lost writes. Ranking is a blend of signals: global popularity, recency, personal history, and context. Most systems precompute a ranking score per query prefix pair offline using MapReduce or Spark jobs. Real-time personalization adds an extra fetch from user profile cache. This ranker merges global and personal completions with weighted scores. In production, scores are pre-computed, real-time merge only for personalization. Don't compute ranking scores online, pre-compute and store top K per prefix in the trie node. Autocomplete is the poster child for multi-layer caching. You'll typically see 3 layers: browser cache, content delivery network for top 1% of prefixes, RIDIs for hot prefixes, in-memory L1 cache and application server, and the trie itself as the source of truth. Here's a simple L1 cache using Guava's cache builder with a maximum size of 10,000 entries and a 30-second TTL. On a cache miss, it falls back to RIDI's L2 and populates L1. L3, trie, is only hit when both L1 and L2 miss. A single server can't hold the entire index. Shard by first 2-3 characters for prefix locality. Consistent hashing minimizes movement when adding shards. Replicate hot shards to handle skew. This shard router uses murmur hash on the first 3 characters to select a shard group, then picks a replica round-robin. Consistent hashing is preferred for minimizing reshuffling on scale-up. This is the same issue we highlighted at the start. A real incident from a large e-commerce platform, autocomplete started showing offensive suggestions for normal queries. Root cause was a cache poisoning attack. Attacker sent malicious queries that got cached, then served to all users. Here's exactly why that happened. Engineers assumed the autocomplete trie was read-only and could not be poisoned because suggestions came from aggregated data. They missed that the system accepted new queries directly into the cache layer without validation. No output sanitization before caching. The autocomplete service stored any query that appeared 100 times in the last hour into the trie and cache without checking its content. Attackers sent offensive queries with high frequency to trigger caching. The fix required purging all caches and adding input sanitization before caching. We added a toxicity filter, TensorFlow-based model, to all new query ingestions, implemented a cache versioning system to allow rollback to a known good state, and rate-limited query ingestion per user IP to 1,000 hour. Never trust user input. Sanitize before storing in any data structure. This is the exact mistake that caused the incident. The system cached suggestions without validating the output. Always sanitize output before caching, strip profanity, PII, and SQL injection patterns. Use a separate freshness score for user-generated queries versus aggregated popular queries. When a rare prefix is requested simultaneously by many users, multiple servers will miss cache and hit the try simultaneously. Use mutex per prefix key, first one locks, others wait. Go's single flight pattern or Java's loading cache handles this. Prefix hashing works well only when prefixes are uniformly distributed. In English, prefixes dominate. If you use 3-char hashing, the asterisk shard will handle 40% of traffic. Fix: use consistent hashing on the prefix hash and replicate hot shards. Don't compute ranking scores online. Pre-compute and store the top K per prefix in the try node itself. Online merging should only add personal context. Otherwise, your P99 will exceed 200 ms. Skewed prefix distribution causes hot shard. Monitor P99 latency per shard. Auto-scale replicas for hot shards, but watch for cross-shard queries. Writes must be idempotent, retry on WAL to leader shard, then async replication. The article's try node uses a hash map per node, which in Java incurs significant memory overhead, e.g., ~72 bytes per entry plus node object. For 100M nodes, this can exceed 20 GB, not 10 GB. Consider using an off-heap or compressed try, e.g., roaring bitmap or byte arrays to reduce memory footprint. The article mentions bounding top K heaps but doesn't show it. Here's a try node that maintains a fixed size min heap for top K completions, ensuring O log K insertion and preventing unbounded memory growth. The article describes cache poisoning, but doesn't emphasize that the attack exploits the fact that the system writes user-submitted queries directly into the cache without validation. Always sanitize and rate limit input before it enters any caching layer, and consider using a write-through cache with a validation proxy. The article mentions consistent hashing, but doesn't explain why it's preferred over modulo hashing. Consistent hashing minimizes key redistribution when adding or removing shards, which is critical for autocomplete because reshuffling can cause massive cache misses and latency spikes. Use a ring with virtual nodes to handle hot shards. Here's a quick debug cheat sheet. Check shard load with curl, inspect logs for specific prefixes, monitor RIDI's hit rate, and use JStack to diagnose cache manager issues. For cache poisoning, check recent cache writes and temporarily disable cache writes while enabling toxicity filtering. Let's run through some common interview questions. Design autocomplete for Google. Use try, shard by prefix hash, multi-layer cache pre-compute ranking. Try V's prefix hash trade-offs. Try O, K, lookup, high memory, prefix hash O1, less memory, hybrid works. Handle cache invalidation for trending queries. Use cache versioning, Bloom filter for affected prefixes, TTL with mutex. And a few frequently asked questions. What is autocomplete? System that predicts completions as you type, using try and caching. Why try over database? Try gives O, K, lookup, no sort overhead. Database-like query is slow at scale. How to handle multiple languages. Use Unicode try nodes, shard by locale, ngram for non-space languages. To recap, autocomplete is a prefix matching problem solved with tries, sharded by prefix hash for scale. Multi-layer caching is essential for sub-50 ms latency. Ranking should be pre-computed offline, and always sanitize output before caching to prevent cache poisoning. Rate limit query ingestion to keep suggestions relevant and safe. Ready to go deeper? Up next, design a payment system, then design a live video streaming system, then design an e-commerce platform. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.